Now let's do the example number 5 of in this course of the transformers. Now the example says a 50 kilovolt ampere, 2400 volts on the primary, 240 volts on the secondary of the transformer. Those are the rated voltages. Has a core loss of 200 watts at rated voltage and a copper loss of 500 watts at full load. It has the following load cycle. So this is a table of which you have a transformer in your neighborhood or in your ghetto that your neighborhood is using, and this is how it is used. Now we have to determine the all-day efficiency of the transformer. Now you can see that we have a power factor and how much hours did we use the transformer in your neighborhood. So I mean, the example doesn't say in your neighborhood. I just want to use your imagination, so it could be a little simpler to understand this. Now you have a transformer, and for 6 hours it has a load of 0%, so no current is drawn on the secondary of the transformer, so no power factor, and there is nothing over there. But and that was for 6 hours. Now in other 6 hours we use 50% of the rated voltage of the rated current for 6 hours with a power factor 1, and so on and so on. Now how do you determine the all-day efficiency of the transformer? So the all-day efficiency AD, so here in this index AD means all day. We can calculate it with the output energy divided by the input energy. So this is a power transformer that is supplying your neighborhood with a variable loads. That is normal because, for example, when it is night, you all go to sleep, and therefore a lot of people don't use electrical energy when they sleep. But if it is noon, or if it is at 12 p.m., everybody uses, I don't know, some kind of electrical energy. And we have to calculate what is the all-day efficiency. And this is the cycle of that transformer. So this is the formula. Why we can't use P out divided by the power output divided by power input? Because the power is changing rapidly. So we have to calculate what is the energy output times the energy divided by times the energy input, and that is the efficiency. Now for example, here is the diagram. So here we have energy input. One of that energy goes to the losses on the transformer that we cannot use in our neighborhood, and the rest goes to the neighborhood. Now, as you can see, the formula for the energy input is equal to output energy plus the energy losses. Okay, now what is the formula for the energy? Well, the simple formula is in this situation is out times the time that we use that kind of power. So the energy output is equal to the power output times the time. Okay, now you know that the power output, we did that in my previous videos. The formula for a power output is the voltage on the secondary times the current on the secondary times the cosine of theta times the power factor. Now this is, for example, okay, now the rated power is equal to 50 kilovolt ampere or kilowatt. This is the apparent power, but never mind. Now this is the rated power, so this is at the 100% of the load. So we don't need current to calculate what is the energy on the 50% of the load, because as you can see, the output power changes with current. So if you use the 50% of the current, then the power on 50% is just equal to 0.5 times the rated power. And the energy on the 50% is just equal to the 50% power times the time that we used this power, and that is 6 hours. And you know that the unit for energy is joule, but in this situation we're gonna use kilowatt hours, because you know joules are big units. So in industry, in real life, as an electrical engineers, you always use kilowatt hours. Okay, I hope you understand now what I was trying to say. So we have to calculate what is the energy output in this day divided by the energy output plus the energy losses. Because here is the formula. Oh, sorry, pay out. Here is the formula for the energy input, and this is the easier way to calculate the all-day efficiency. I'm just gonna remove all this here. And that is that. Now let's calculate what is the energy output in this particular situation. So the energy output. So now you know that the so here in this for this first 6 hours that we have, we don't have any load, so no current is drawn on the secondary, so no current goes on the secondary, and the energy for these 6 hours that we used on the secondary is equal to 0. So in this particular situation, I'm not going to write anything for the energy output. For another 6 hours, we use the 50% of the load from the transformer. You know that from the rated power, we used 50% of the rated current. So now we are going to write 0.5 times 50, the 50 kilovolt amperes. We're not going to write kilo or times 1000, you will see why. Times, so we need the load percentage, that is, you know, 50% in real number is 0.5, and times 50 and times the number of hours that we used, and that is 6. Plus, now we are going to this particular situation. Now we are using 75% of the load, but we are using 0.8 power factor. You know that the output depends on the current, the voltage, and the power factor. Now, in this cosine of theta. Now, in this particular situation, cosine of theta was power factor was 1, so I didn't write times 1, even though I could. But in this, you know, you have to now multiply 0.75 times 50, that is a rated voltage, times, I'm gonna write this in another column here, row, sorry, 0.75 times 15 times the power factor. So the output power depends on the power factor. So that is 0.8 times the number of hours that we used, and that is 6. Plus 100% of the load. So this is for the current. We can write down 1 if you want, but I don't have to. We have 0.9 power factor lagging, so we are going to write 50 times 0.9 times the number of hours, that is 3. Plus, over here, we have 110% of the load with power factor of 1. 110% in real number is 1,1 times 50 times the number of hours, and that is 3. Now, I said that we are not going to write down 50 kilo because in this, now I'm going to write, but we can put all this in here, brackets like this, and then we can multiply everything with 1000 or 10 to the third, because every here part of the every part here has kilo, so I didn't write down kilo, 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 or kilo, because if you multiply this everything what is in this bracket with 10 thirds, this goes on this, 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 and this. So now Now I'm going to calculate everything here, and then I'm going to multiply this with 10 to the third, or I'm just going to write this. This is kilo, so I'm just going to write kilo. But I just want you to know what is going on here. And the unit is kilowatt hours, not joules. So if you wanted to do in joules, then you would have to the joule is equal to watt times second. So if you want joules, then you would have to multiply 6 hours with 3,600, because there is 3,600 seconds in 1 hour, and that's why we use watts, kilowatts, hour. Okay, now let's go. 0.5 times 50 times 6 is 150, plus 0.75 plus 50 times 50 times 0.8 times 6 is 180. Oh man, I'm so sweaty here. It's really hot. 50 times 0.9 times 3, that is plus 135. 0.1 times 50 times 3, that is plus 165, and everything that we divided by 10 to the third. Now 150 plus 180 plus 135 plus 165. That here, this is, okay, I'm gonna write this. So in these brackets, this the value of all these summation of all the additions of all these numbers is 630 times 10 to the third watt hours. So this is the unit that we used. Now 10 to the third is kilo, and we are going to write 630 kilowatt hours. And that is it. Now we calculated the output energy. Now we have to calculate the output or the energy losses in this transformer, so we can determine the efficiency of the transformer. The losses, the energy losses of the energy losses in the transformer goes in the core losses and the copper losses. Now we are going to calculate the energy losses in core losses. That is very easy. Now the energy losses, if on the primary side of the transformer you have a constant voltage. I don't know if you remember the equivalent schematic of the transformer. And the equivalent this was the equivalent schematic or circuit for the transformer. Now, if you always have a rated voltage on the input, a small current is going to go in this branch over here. This is the magnetizing branch, the shunt branch. I don't know how every literature says it differently. And small amount of current goes, and it is always the same. So no matter what kind of if you have, I don't know, million% of the load of the current, you will always have same magnetizing current that magnetizes the transformer. So the voltage, the power losses in the core losses depends on the voltage input squared. Now, if you always have the same voltage in 24 hours, if you always have on the primary side the same voltage, then the core losses don't change, and the core energy losses in the core of the transformer is equal to 200 watts, but I'll transform this in kilowatt hours times 24, and this is equal to where is my calculator? 4.8 kilowatt hours. Now, this is the energy we lost, the energy of the transformer in your neighborhood. 4.8 kilowatt hours is lost just in magnetizing the core. So no matter if you had 0% load, no matter what the power factor is, if you have a constant voltage on the primary side, you will always have a small current that goes here that will magnetize the transformer. And even though if you have no load, some of the current will go to magnetize the transformer. And if you have a constant voltage, the core losses don't change, and this is the energy that we lost. So I transferred 200 watts into kilowatts, so that is 0.2. times 24 hours, and then you get 4,8 kilowatt hours. So I hope you understand what I did over here. 200 watts is 0,2 kilowatts. So if this kilo is 1000, so if you have 0,2 times 1000, you get 200 watts. And then I calculated 24 hours, and then 0,2 times 24 is 4,8 kilowatt times hour, kilowatt hour. If you don't understand these measurements, that's why I wrote it down. Okay. Now the copper losses that goes on the conductors. The formula is I squared times R. Okay, now, so if you have a changing load, then the copper loss is going to depend on the current but squared. So now we will calculate the energy in the copper that is lost in the copper of the transformer. And now, here in first situation, we don't have any current that is drawn from the primary side or on the secondary. So you would have to say 0 squared, but 0 squared is 0, and in this particular situation I'm not going to write anything down. And 500 watts I'm going to write it as 0.5 kilowatts. I hope you understand why. Now, in this situation, we have 50% of the current, then we are going to write down 0,5 squared, because the copper losses depend on the current but squared. Now, times the rate, 50% of the rated loss, copper power loss, that is 0.5 kilowatt. Times the number of hours, and that is 6 hours, and that is that, plus 75%. 75% of the load, that is 0.75 squared. Now it says 0,8 lag, but it doesn't depend. In this formula you don't have cosine of theta, so no power factor, so it just depends on the current. 0.75 of the rated copper loss, so 0. Times 0.5 times the number of hours, that is 6, plus 100% of the current, but that is 1 in real number. So 1 squared is 1. You don't have to write 1 squared. If you want, you can write it down, but I will not do that. Times 0.5. 1 times 0.5 is 0.5 times the number of hours, that is 3. Plus 110% of the load, that is 1.1 squared, times the power, that is 0.5, and times the number of hours, it is 3. I'm just going to continue writing this down over here. Now all you need is a calculator to calculate the value of these numbers over here. So 0.5 squared plus 0.5 times 6. So here we have 0.75 kilowatt hours. 0.75 squared times 0.5 times 6, that is equal to plus 1,6875. 0.5 times 3, that is 1 plus 5, 1,5 plus 0.1 is, I don't know, 121. Yes, times 0.5 times 3, and that is equal to 1, I'm just gonna write it here, 1,815. So all this here is in kilowatt hours. And all you have to do is add all these values. And that is equal to 5.7525 kilowatt hours. So in this particular situation, the energy lost in copper or in the conductors of the transformer is this. Let me just see if that all is good. Yes, it is. Now the energy losses is the core losses and the copper losses. This plus this is equal to, so 4.8 plus 5,7525. In this book, that is roughly 10,556 kilowatt hours. That is in the book. Now the energy losses in the transformer is this. Don't need this anymore. I need this. Don't need this anymore. Don't need this. Don't need this. So now we can calculate what is all the efficiency. Now the output here is 630 kilo, but everything is in kilos, so I don't want. Okay, let me just do this for you. 10 to the third is kilo. Energy output plus energy losses. We have kilo everywhere in this fraction, so we can do this, and the efficiency is 0.9835. But if you want to write that down in percentage, that you just multiply this by 100 and add the percentage sign. And that is that for this example. Thanks for watching, and see you in my next video where I'm going to show you what is an auto transformer. Bye.